Hello, this is the second video for Graphs and Networks Series 3 on Further Graph Theory for OCR Discrete Further Mathematics. And we will look at Hamiltonian graphs. Let's recap on some terminology. A graph is a series of nodes or vertices connected by edges or arcs. And a path is a trail in which no nodes are repeated. So, an example in the diagram below might be A, E, D, and C. A cycle is a closed path. So we could start at A and go along to B, then down to C, up to E, and then back to A. A Hamiltonian path, or traceable path, is a path in an undirected or directed graph that visits each vertex exactly once. If a Hamiltonian path ends at a vertex that is adjacent to the initial vertex, then it is a Hamiltonian cycle. Here on the left-hand side diagram, we can find a Hamiltonian path, but not necessarily a Hamiltonian cycle. So if we start at C and we move to D and then down to E and F and A and B, we have visited all the vertices, but we can't get back to C. However, on the right-hand side diagram, we could, for example, start at A and travel to B, and then D, and then G, E, go to F, and then to C, and then to A. So you can see that that is an example of a Hamiltonian cycle. And a graph that contains a Hamiltonian cycle is called a Hamiltonian graph. Note that there is no simple test for distinguishing between Hamiltonian graphs and non-Hamiltonian graphs. And it is generally also not simple to identify Hamiltonian cycles in graphs. But you can identify some of the different Hamiltonian cycles in a small graph by inspection. So we could go from A to B to F to D to G, and then to E to C to A. Let's see if we can find a different one. Well, we could go A, C, E, and then G and D, and then F, B, A. But actually, you can see that although the order of the letters is different, it's the same. And similarly, if we'd started at F and gone D, G, E, and then C, A, B, F, it would have been the same Hamiltonian cycle. Let's try again. What if we go A, B, D, and then maybe G, E, F, and then C, A? Was that any different? And the answer is yes. So there are at least two different Hamiltonian cycles in this small graph. Let's try and find a Hamiltonian cycle on this graph. So starting from here, I'll work my way around the edge nodes and then turn in. And then I think I'll go in around that lot of nodes and then out and then back up. So yes, I found a Hamiltonian cycle. And here, more clearly shown, is an alternative solution. So there are probably quite a few. So a cycle that visits each vertex once and only once, including all the vertices of a network, is a Hamiltonian cycle. On this graph, starting at G, we could travel D, A, B, C, F and E, but we cannot get back to the initial vertex, so therefore we have a Hamiltonian path but no Hamiltonian cycle. However, in this graph down here, which we note is the complete graph K5, wherever we start, let's try A, we can go B, C, D, E and back to A in a Hamiltonian cycle. In fact, all complete graphs have Hamiltonian cycles. In network problems in the next series, we'll look at finding the minimum total weight Hamiltonian cycle to solve the travelling salesperson problem. In the next video, we introduce Orr's theorem.